I'm going to take this out and do a walk and talk because then I'll feel like I'm on the West Wing. So thanks for the introduction. I am Dave. I am a project manager with Frontier Power Systems, and so I guess what that means is I wear way too many hats in a smallish engineering firm growing into a medium-ish engineering firm with manufacturing and technology development. This photo back here is in Ramia. It's a island outport off the south coast of Newfoundland, and when I was a kid, Dad mortgaged the house. He bought 6 used wind turbines. He rebuilt them. They're right there, and he started Frontier Power Systems. And this picture is back in 2003 when those turbines were being installed. Now, before the turbines came in, Ramia, like almost every community, every remote community around the world, was powered through diesel generation. And in 2004, when this project came online, it was the first medium displacement wind diesel system in North America. It's still operating today, and we are on track actually to have our most productive February to date, although the leap year might play a role in that. But that's something to be proud of because we're entering year 17 of these turbines' second lives. And this photo here is taken in Kipnuk. It's on the Bering Sea in a remote part of western Alaska. And these UPIC gentlemen, they are installing rebuilt Windmatic 17S turbines, or they are 100 kilowatt turbines that we shipped out there a few years ago. This photo was taken in 2018. And so from across northern North America, from Alaska to Greenland, and then down into Quebec and Newfoundland and Labrador, there are over 350 communities. The vast majority of them get their power exclusively from diesel generation. Now, things are vast up here, both in distance and time. From, where's my pointer? From Ramia to Kipnuk is 6,400 kilometers. And those two photos I showed are 15 years apart. Things have moved slow in this industry for a number of reasons. And when we got started, things were a lot different than they are today. When Frontier got started, climate change was a concern, but we all thought it was 40 to 50 years away. The big concern was oil. We thought we were going to run out of oil before we ran into climate change, and diesel prices were going to go through the roof. Well, now today we still keep somehow managing to find oil, and climate change didn't get the memo to wait another couple decades to show up. So these communities that cover this part of the planet are at the forefront of this change in climate, and access to energy is going to play a big role in the stability of these communities moving forward. So in order for us to get from where we started in Ramia to where we are today, with most of our projects being in Alaska, we had to overcome a number of technical hurdles. The first thing we overcame after installing the turbines in Ramia were developing advanced controls. Now, in Ramia, Newfoundland Labrador Hydro controls the diesel plant. All we do is generate electricity, send it to them, and they take care of managing the load, they balance the frequency, they balance the voltage, they keep the load happy. But we wanted to develop advanced controls that could do both those things. So in 2008, we worked on the Hydrogen Village project with the PEI Energy Corporation. It was a demonstration project to see the feasibility of hydrogen as an energy storage mode. So what we did is we established a base load that we called our village, and we supplied that load with power through wind turbines. When there was excess energy available from the wind turbines, we pumped water, did the electrolysis process to break it up into hydrogen and oxygen, stored the hydrogen, and then when the winds decreased, we burned that hydrogen in a generator and converted it into electricity. It was a worthwhile project and demonstrated a couple of things. First of all, it demonstrated that come 2009, hydrogen storage technology still wasn't where it needed to be. But it did allow us to develop an advanced control algorithm that allowed us to control the load using multiple power sources autonomously and in real time. So fast forward a few more years in 2011, and in a moment of serendipity, an old contact of a dad's from Alaska, Dennis Miners, called him up and he said, "Carl, I got a problem. I'm putting turbines in 3 communities. They have wind diesel systems already, and they're all getting 5 100 kilowatt turbines. So we got diesels, we have turbines, and we have no way to integrate the two and make them work together. Can you help us out?" And so we did. We took what we learned in the Hydrogen Village and applied it to these 3 villages: Tuntatuliak, Kongiganac, and Quigilingok, which we affectionately call Tunt, Kong, and Quig. You can see them there along the Kuskokwim River Delta. There's Quig, there's Kong, there's Tunt, not too far from Kipnuk, where we shipped turbines in 2017. And up there is Bethel, that's the hub community. So we have to take flights to Anchorage, a commercial flight to Anchorage, and then we take bush plane flights out to these communities. That was quite successful, and since then we have worked in, are working in another 9 communities in western Alaska, with more of Alaska coming online in the next few years. And our system has grown and become more robust, and we've come to name it the E+ microsystem. So here's a schematic of overall general view of how the E+ microsystem works. It's broken up into two groups of components. There's the integrated components and the distributed components. The integrated components are up here. It's the System Master Controller, which we call the SMC, and the SCADA computer. The SMC is the brains of the operation. It monitors the village load, down here, and allocates resources as available as optimally as possible in order to satisfy that load while maintaining high power quality for the end user. The backbone of the distributed components are the diesel generators. Even in these communities today that have wind power, the diesel generators are still carrying the majority of the load. They're also balancing the voltage and the frequency. We have the wind turbines here on the left-hand side, which provide electrical energy to the bus and then to the village when available. And above the diesels, we have what's called the load regulator. It's a very important tool. It acts as an instantaneous power sink. See, whenever the wind picks up and the turbines start generating more power, the diesels inevitably generate less power. But the diesels get to a point where we don't go any lower. We call that the minimum operating load. If we go lower, then we're going to run into risks of damaging the engine. So what happens in that point if the load on the village doesn't change, but the wind turbines supply more power? We send that power to the load regulator to be consumed as a fail-safe. Another way we can deal with energy storage is through the electric thermal storage devices, the ETS units. These are salt brick oven stoves, and kind of related to what Andy was talking about. These are in different houses around the community, and whenever there's excess electricity available, we can send the electricity to these salt brick ovens, charge them up, heat them up to about 2100 degrees Celsius, and then the folks in those houses, when they come home, they have a second option for heating their houses other than oil. And then finally, the big game changer is the BESS, the battery energy storage system. This is what Tesla's doing with their Powerwall and with that big battery they have in Australia. Now, two of those first three communities, Quig and Kong, have a BESS. I said earlier that Ramia was our first medium displacement wind diesel facility. A BESS allows us to go from a medium displacement facility to a high displacement facility. In Ramia, no matter how much wind is blowing, the diesels can never shut off because they have to balance frequency and voltage. And they have to be available to come online at a moment's notice if the wind drops. But the BESS does balance frequency and voltage and can carry the load for a significant amount of time to bring the diesels back up to speed in the event the wind drops off. So we see this. This was taken on a day in April in 2015 from the village of Quig. It's about a 36-hour time frame here. So what we saw shortly after midnight was the load on the diesels came down. Part of that was because people are in bed, but a bigger part of that was because we see underneath the diesels that the wind started to pick up. A wind system moved into Quig and was there for a day and a half. Probably around 7 a.m., the system master, which was monitoring the load, monitoring the diesel output, monitoring the status of the BESS, and monitoring the wind resource, said, we're good, let's shut off the diesel. So they did, and the diesel stayed off for about 24 hours. Now, while the diesels were off, you can see the wind stayed high while the system was around, and the BESS helped balance the load. It injected power into the system whenever the winds were in a lull, and it absorbed power from the turbines whenever there was more power available from the turbines than the load demanded. And underneath the BESS, we can see how the load regulator operated. It did some corrections during the time when the BESS was operating, but the BESS carried the majority of that. What it really did was, just before the diesels turned off and right after the diesels came back on, the load regulator showed its worth. This would have been when the diesels were at minimum load, the BESS wasn't ready to come on, the wind had picked up, and the load regulator had to absorb that power. These are some more graphs of the same system. The wind on those same days looks identical, and the BESS identical to the previous page. But here we can also see the ETS units. So the ETS units are being charged here. So again, when people come home from work or from home for their day, come home from hunting, they're able to heat their house with the ETS stoves. On the second last graph, we can see the frequency. And we also notice that the BESS does a better job of balancing frequency than the diesels do, which makes sense. The diesels have to balance frequency by mechanically throttling back and forth on the gasoline or the fuel they're putting into the system. The BESS can do it much more quickly. Also, the BESS balances the voltage load of the system. There is a slight drop. I've never had a satisfied answer as to why that drop existed, but it does a good job of balancing the voltage and turning off the diesels. So that's the first part of the integrated components. The second part is our SCADA. Our SCADA monitors the system, and it's our window into the system to interact with it for us and the operators in the villages. This is the HMI, the human machine interface for Congiganak. Now, every village is unique, so every HMI ends up being unique. On this day, we had all 4 diesels shut off. 1 and 3 completely shut down, 2 and 4 were in standby mode in yellow, and you can see below them the load regulator carrying some of the load, and that heat from the load regulator was used to keep the diesels warm so they could turn back up when needed. All 5 turbines are operating, but the winds are only just below 8 meters a second, so 100 kilowatt turbines, they're not quite putting out 30 kilowatts each. Still, it's enough to carry the village load and enough to charge the BESS. Now, from these screens, we can go in to the individual turbines, we can reset errors, we can look at energy and historical data, but this is the main one that we see. This is what the turbine, or this is what the diesel plant operators see whenever they're in these villages operating the diesels, and we access these remotely from anywhere with an internet connection. Now, the SCADA also stores data, and it stores a whack of data, and the amount of data it stores has led us to take a lot of evolutionary steps with our SCADA systems. But one thing it allows us to do is paint a pretty clear picture of what's generating power, when it's generating power, and how it's offsetting. So we produce monthly and annual reports of energy generation, and this is from Quig for a 2019 summer report. We can see that what the diesels produced, what the turbines produced, and what the consumption side consumed. Diesel 1 never came on once last year, and that's pretty typical in these communities. Generally, you have 1 or 2 diesels, that's the workhorse. The other 1 or 2 diesels are there just as redundancy. Also, Quig had problems with T2 last year. I think it was a yaw drive issue, but it never came on. With the remoteness of these communities, if you have an issue becomes a big issue because it's not like there's a Kent down the road where you can go and buy supplies. One important factor down here at the bottom is the percent of displaced kilowatt hours by the wind on the diesel, which is just under 24% for Quig. That's actually not that good. In Cog-Gigantic, we sent a BESS system up in August of 2018, and we're seeing 50% displacement. Before there were turbines in Kong, they were burning through 150,000 liters of diesel fuel a year. Now they're consuming about 70,000 liters of diesel fuel a year. And that's a big deal, not just environmentally and financially, but culturally. These communities have been here for hundreds or thousands of years, and shortly after, sometime after the war, they had diesel generators hauled in, and they turned them on, and there's been a diesel generator operating in the background, humming along since then. And so this silence has become somewhat eerie for some of the people who live there. Anyways, that covers the integrated components of our E+ microsystem, but there's also the distributed components. The integrated components are continuing to evolve, but we've implemented them in a number of communities, and we like where they're at. The next thing we had to focus on was the distributed components. Now, when we got started in 2002, there were probably a half a dozen turbine manufacturers around the world who were building medium-sized wind turbines for these markets that we need. But then in the early 2000s, wind took off for the better, and people realized that to make money in wind, you'd go to a utility scale and get bigger and bigger wind turbines. That's good, but it ended up pushing a lot of these medium-sized wind turbine makers out of the picture. So we realized shortly after we started doing these systems that integrating these systems is wonderful with wind and diesel, but nobody has a cost-effective wind turbine, so who's going to do it? So we decided, well, we're going to have to do it. Then the question became, well, how do we do it whenever we're a very small engineering firm on PEI? And the answer is through a lot of iterations. So the first thing we did is we went down to California and we allocated a bunch of old Windmatic 17S 100 kilowatt turbines. They needed some TLC, but we brought them back to our shop in PEI and we rebuilt them as new. We changed all the bearings, we changed all the seals and the gearbox, we changed all the gears, we retrofitted the generators, all that. On top of that, we also gave them an advanced control system and put a VFD on the wind turbine. The VFD allows us to capture energy at the lower wind speeds, increases our capacity factor. In 2017, when we sent 6 wind turbines to Kipnuk, we sent these rebuilt turbines as our Mark I offering. The next thing we wanted to do was redesign the tower. Now, because of the remoteness of these villages, construction costs are very high. In the Alaska areas that we're working right now, they get 2 barges a year. And if you miss the barge in July, you have to wait till the following May to get your equipment into the town. So if you want to build a turbine, you got to allocate a crane for almost a full year just to do a couple weeks worth of work. So we said, let's get rid of the crane. And we developed this tower, which tilts up using a winch and a gin pole. And that's our tower being installed in East Point. Anyway, so that's our tower being installed in
in each point. So not only does it get rid of the cost of the crane, but it also puts the rotor up 50 meters instead of 25. It gets us into the higher wind regimes, which again increases our capacity factor. After that, the next thing we said was, oh yeah, let's build some blades. So we figured out how to build blades. We worked with ETS, the School of Montreal, to design them. And then we bought a shop in Georgetown, PEI, and in August 2017, went about figuring out how you build blades. That was a long process, but a pretty fun one. You can see here, the first step is to lay up the blade with glass fiber, carbon fiber, and foam, and then we do a vacuum infusion with epoxy resin. We make 2 blade halves and some other components. We trim the blade halves, get them all dolled up, put a shear web in them, slap the 2 together with some glue. We got our blade form. After that, we have to do some more trimming, we have to cook them, we have to sand them, and then this picture here is the few days that Buddy came up from South Carolina and taught us how to paint blades, which is a pretty complicated process. In March 2018, we had our first 3 blades come out of our shop. They are now on our prototype, and since then we've built quite a bit more. The blades have been a big step up, because we've gone from a 17-meter diameter rotor on the original Mark I to a 24.4 meter diameter rotor. And with pi r squared, that means that the swept area that we're capturing has almost doubled. So we've got a VFD, we've doubled the swept area, and we're at a higher elevation on the tower without a crane. So the cost of these turbines are slowly coming down. And that's a comparison of where we started versus where we are right now in Mark II. We sent 3 Mark II turbines to Shippornak in Alaska last year. We've got another 5 to come out of our facilities and be shipped to Alaska this year. The final design process for our turbine is to redesign the drivetrain and put a modern drivetrain on that. That design's well underway. It's looking extremely promising. We're hoping to start casting in the next couple months and expect to have our first prototype on our prototype tower at each point by fall of this year. Anyway, so the long and short of it is it takes a long time to build these markets. They've been underserved for a while, and it's a lot of technical challenge to overcome. And we have overcome a lot of them, but we've been around long enough to realize that we haven't overcome them all. But with that being said, there's a lot of reasons to get up in the morning. The commitment to decarbonization keeps us going, but also the fact that there are 2 billion people on this planet who have yet to have access to a full-size grid is also another reason for us to get up in the morning and keep trying to solve these problems. Oh, thank you very much for your time. I'd be happy to answer.